Hello, class. Welcome to a new chapter of the textbook. In this video, we are going to start chapter 4 by looking at Riemann sums. So we are going to introduce Riemann sums in order to get to uh, concept of integral. So the purpose of this video, this study is to see how can we use Riemann sums to estimate the area between a given curve and horizontal axis, and also what are the different methods to find that area, and also how we can use how can we write those in terms of specific notations. So in general, if you have an object that moves on with a positive velocity, and you have the graph of that velocity, like this image, you look at this picture. So this picture shows a graph. The graph is in blue, the blue curve, right? And suppose this graph is the graph of a velocity function. So it's like we have an object, it's moving with a positive velocity, and the v of t is just the graph of that velocity, and the horizontal axis is the time. So it shows us the moving object over this time. So then, if we want to find the distance traveled by this object over a specific period of time, we can just find the area under the curve. The area under the curve up to the horizontal axis, like in this picture, let's say the object moved over the time interval of a and b, and the blue curve is the velocity. Then if you want to see what's the distance that is traveled by this object, it's just we can obtain that by looking at the area under the curve, which is highlighted here as a1, a2, and a3. So this is the reason that I just wanted to tell you that this is one of the reason that we are interested in area under the curve. Okay, so for questions like this, for topics like this, we would like to find the area under the curve. And uh, and one more point before moving on. So if you have like a1 and a2, which is the area under the curve, that area, that region is located above horizontal axis. We take that area as the positive, and if the region is located under the horizontal axis, we consider that as negative. So what I mean here, let me show you what I mean here. So in terms of application, look, so if you have an object, so you have an object that is moving on some path, right? So this is a path, and your object is moving, and you want to see what is the distance. Let's say this is time A, and this is time B, and you are interested in distance traveled by this object, right? So you are interested in this. So if you have the velocity graph, suppose, let me look at this graph. Sorry. So you have something like this. So this is the velocity of this object, this movement. Then let's say this is A, and this is B, and you want to find the area under the curve. So you want to find that distance. If you find the area under the curve, that gives us the distance. So the area under the curve up to the x-axis is this. Now let's call this A1, A2, A3. So the total area is sum of A1 plus A3, but because A2 is under the x-axis, we subtract it. We consider it as a negative value, right? So this total area is the distance traveled by the object in this scenario, right? So as you can see, I mean, in physics, like we might be interested in questions like this: to what is the distance traveled? If we have the velocity of this movement, then what is the distance traveled by this? And in order to answer a question like that, we need to evaluate this area. But what's the problem? The problem is that, okay, if you want to know what is A1, we need to calculate this area. And look at the shape of this area. It's, okay, this side is a straight line. This side of the shape, the region is a straight line, but this side is a curve. So the shape, we need to find the area of something like this, right? In geometry, we need to find the area A1 is, we need to find the area of a shape like this. But in geometry in high school, what type of, so we learned, we know how to calculate, how to compute area of like square, rectangle, circle, triangle, and other like basic shape, but we have just limited shape that we know how to calculate. We have a formula to calculate the area. But for example, if you have something like this, and you want to find the area under the area of a region, we don't know. There is no formula. There is no formula. We don't know any formula for this area, right? So there are some, like here in this graph, in this question, we need to find area like this, right? We don't have a formula to find that. So that's the reason that we are going to define Riemann sums, because there is no formula. There is no way that we can find the exact value for this area. There is no way we can find the exact value. So we have to estimate it. So we have to estimate this area. How? Using the area that we know. Look, in high school, we just learned the area of like a square, right? A triangle, circle, rectangle. So that's the only ones that we know. For example, area of circle is pi r square. If this is A, then the area of a square is A square. If this side is A, this side is B, then the area of rectangle is A times 3, right? So these are the formulas that we know, and we have to, we don't have any more option. We have to use those in order to estimate the area of this rectangle. So that's the idea. We need to compute areas that we don't have a formula for. There is no formula for those. And for that reason, we are going to estimate those areas using, in particular, rectangles. So let's look at the activity, preview activity 4.21. Here, okay, so in this activity, we are going to look at this scenario that a person walking along a straight path has her velocity in mile per hour at time given by this function. So we have the function for velocity, which has this formula for times in the interval of 0 to 2, which means 0 to 2 hours. And so here is the graph. In this figure, you can see the graph, but you see three images, which I'm gonna explain each one of these images and tell you what does each mean. Okay, so look at the first graph. The first graph, maybe I should copy this image because I'm gonna explain it. Let me see if I can paste it here. Yes. So in the first one, we have the graph of the velocity function. And so the blue curve is the velocity function, this blue curve, right? And then we want to find the distance traveled by this object over time interval of 0 and 2, right? So we know that the distance between 0 and 2, between 0 and 2, the distance, we know that the distance between the distance traveled by this object between from the starting point until the 2 hours is going to be the area under the curve. So it's going to be this, right? Okay. So what we need, maybe I draw it here. Look, here is time, right? And then we have a curve like, let me see. So we have a curve like this. So at 0, the object, the velocity is here. At 2 is here. So this is the velocity function. So we know that the distance traveled by this object can be obtained by this area, okay? This area. So if we can find this area, so this highlighted area, this area gives us the distance traveled by the object. So we need to find this area, right? We don't have any formula to find this area, but we can estimate it. So we are gonna estimate this area. One way to estimate this area is by using these 4 rectangles. Look at here, we have 4 rectangles, and we call them A1, A2, A3, and A4. So because we know how to calculate the area of rectangle, so we can calculate A1, A2, and A3, and A4, and then we add all together, right? This is gonna give us an estimation of these areas, but it misses some part, you see. So for example, it's gonna miss this part, right? It's gonna miss this part. It's gonna miss this part. So this is an estimation of the area. However, it misses some part of the area. So if you add that, let's call it S. Let's call it S. Then S, this number, is an estimation, can be looked at as an estimation of the area that we want. However, we know it's less than the real area because it's missing some part of the region. And so this is one way. And the way that we construct these rectangle is that we miss some part. So in other words, we put 4 rectangles under the curve, and we know that it misses some part, but so it's like an underestimate. So this is an underestimate of the area. This is one way of estimating the area. The second way is looking at these boxes. So instead of those A1, 2, 3, 4 rectangles, you can draw 4 rectangles in as B1, B2, B3, B4. Add all of these, because we know how to calculate the area of these rectangles, we can find each one, add them all, and what's the textbook called this? It's called T. And then T is also estimation. T is also an estimator. It's an estimation of the area. But here we are, we have more, look, this is extra. Because area under the curve, this is above the curve. You see, this is extra, this is extra. So this is like an overestimate of the area. Please pay attention that there is no way to find the exact value of this area. So either way, no matter what method you use, this is always an estimation. Now, it's either we are underestimating, which means that the value that we are offering is less than the actual value, or we are overestimating, which means that the value that the number that we are giving as the area is more than the real number of area. In the last diagram, we put 3 other, again, we are drawing 4 rectangles, but it's different than the other 2. For example, look at C1 and C2. So yes, so it's like it's a combination of overestimation and underestimation. For example, it misses, if you add C plus C1, C2, C3, C4, and call it U, U is also an estimation of the area. But the difference is that it's a better estimation of the other 2. The value is closer to the real value. Why? Because yes, it misses some part here, but also it adds some extra value. So it's kind of, it balances. For some part, it misses something from the real area, but in another place, it adds extra words. So it's kind of, it's a balance between lost and losing and gaining area. Look at here. It misses some part here, but also it adds some part here. So it's balance. Same thing here. It misses some part, but it also adds some part. So what happens is that between 3 methods, what is the first method? It's absolutely underestimated. It's an underestimation of the area. What is the second method? It's an overestimation of the area. The third one, the last one, it's a combination of both. We draw the graph in a way that we put the rectangle, that each rectangle has a balance of is overestimation and underestimation. And in this way, the total, the U becomes a better estimation of the area. It becomes, the value becomes closer to the exact value. But I think you got the technique. So the technique that we are going to use is just drawing rectangles. Now, either we go with no matter what method that you use, we go with the rectangles, and then we find the value, the area of each rectangle, we add all together. That becomes an estimation of the exact value of the area. Now, Let's talk about notation because we're adding. You see that in our method, we create several rectangles, and then we add the area of these rectangles. So we have addition, summation, right? So when we discuss about this, we have sum. So when we have sum, we usually use sigma notation. What is sigma notation? For example, let's say you want to add all the numbers between 1 and 100. So you say 1 plus 2 plus 3 plus 4 plus 5 up to 100. The alternative way to denote this summation is using sigma. So we put sigma of one variable, whatever this doesn't matter what letter you use, you can use any letter. For example, k, sigma of k, and then k is like an index. What values does x get? It starts from 1 and it's at 100. So this is just introducing a notation because usually we work with a lot of rectangles. It's not 4 rectangles, so we have to have a notation in order to have an easier way to represent these estimation. Okay, so sigma notation. So what is sigma notation? So for example, when you say sigma of k from 1 to 100, so that means sigma means summation, addition. So add values from 1, start from 1 up to 3. So add 1, go to 2, to 3, to 4, up to 100. So this is the starting point. This is the ending point. And sigma means summation, addition, and this is just whatever the variable. For example, when it says, what else? Look at this. What does this mean? Sigma of, so we are just practicing notation. Sigma of, what's the variable? K squared plus 2k. Now, what are the index? K from 1 to 10. 1 to 10. So what does it mean? So this means, okay, start from 1. So from 1, we have 1 squared plus 2, 1. So this is the first step. Summation. So we need to add now. So this was k equal 1. Now k equal 2, the next term is going to be 2 squared plus 2 times 2. You see? Now, the next term, then k is equal 3. So it's going to be 3 squared plus 2 times 3 plus, and so on. So you keep putting these terms up to the last one is 10. So it's going to be, the last one is, it stops at 10. So it's going to be 10 squared plus 2 times 10. Okay, so you see a summation like this, if you want to, this is the expanded form. You see, this is the expanded format. So it's very long if you want to write this summation. It's very long. To avoid this, we use this sigma notation. Sigma notation to express what we mean in a short and a clear way. So what does this notation mean? Sigma of f of k f as a function. So the output of this, so it's the summation of the output of function k from 1 to n. So it starts at 1, so f of 1 plus f of 2 plus f of 3 up to n. Whatever is n, we stop. So we start from here and we stop here. and we add everything in between. Okay. Here are some couple of activities. Oh, maybe I do one and then I leave maybe I do two of them. I leave the rest for you. So this is the first part is to what is sigma of k squared plus 2 k from 1 to 5. I want to give you the exact value. Okay, so what does this mean? It means start from 1. Okay, so it's going to be 1 squared plus 2. So this is when k is 1. And then add. Now, put the term for next index 2. So it's going to be 2 squared plus 2. Next term, when k is 3. So this is going to be 3 squared plus 2. The next one is next index 4. So this is going to be 4 squared plus 2. And the last one, because we have to stop at, you see, we have to stop at 5. So at 5, this is going to be 5 squared plus 2. Okay, so this is a summation. We need to add these values. So let's simplify it. This is going to be 3. 2 squared, 4 plus 2 is 6. 9 plus 2, 11. 16 plus 2, 18. And the last one, 27. And then you add these values. So it's going to be 27 plus 18 plus 11. And 3 and 6 is 9. 65. Okay. So this was a practice of when sigma notation is given, when a summation is given in the format of sigma, and then you can just expand it and calculate that summation. Now let's express this as the sigma notation. So here the summation is given, which is 3 plus 5 plus 7 up to 27. Wait. No. Okay, no. I should write more. It's 3 plus 5 plus no, there is no 5. Why do I write 5? This is 7. 7 11 15 up to 27. The question is, now you have a summation, right? There is a sum. So look at the question. If sum is written in the sigma notation, then write the sum longhand expanded format and evaluate it. And for the sum written in the expanded form, like this one is written in the expanded form. Now write the sum in the sigma notation. So we have to find a way to express this as a sigma notation. How can we express this sum as sigma notation? نمیدونم ویدیو چی شد. So something happened to the video. Sorry about that.